So, Mr. Chairman, ladies and gentlemen, thank you very much for having the possibility to talk to you. And I want to give you in my short presentation a very small introduction into artificial intelligence and edge computing, how it might be usable in the museum domain. My co-author, Gerda, is probably known to you as aggregator in the Europeana in the biodiversity domain. If you look into artificial intelligence, we have different areas to distinguish, and only concentrating on methodologies which we are using in the example which will be presented afterwards. We have the big part of machine learning, and there's a subset deep learning. In deep learning, we have neural networks. There are different methodologies and different ways how you can create an artificial neural network. And I will bring you a small example how a convolutional neural network can be used. I also have to tell you that I'm not only involved in museum projects, but I'm also doing a lot of medical research and developing biomedical devices. So some of the examples are coming from that domain, which probably could be used sometimes in the museum domain. As one example, how we can use artificial intelligence in the cultural heritage domain. And here I'm referring to a project which was finished, I think, last year. And the topic was analyzing images. And images, we have used a sub-collection of Europeana. And these images had in their content and have been dealing about food. So how to analyze such images, how to connect this image. Here you could use, for example, CRM or any other methodology. And the research project wanted to clarify what type of methodology could be used and what tools are available. And at the end, these images have been somewhat like annotated using these tools. On the right side of this slide, you see an image which was analyzed using artificial intelligence. That's only an example. You can also use this artificial intelligence methodology to analyze videos. For example, you can define a topic. For example, cars. Probably you know Mr. Schwarzenegger, the previous governor of California, I think. He was driving a Hummer, and then you can make probably a selection and analysis of videos dealing with Hummers. I'm pointing to this because I was looking into this methodology for practical use. And one use might be you can annotate and you can analyze images for ill people. If you have people getting dementia, then this type of information in a therapeutical framework might be used to set up a therapy for this. So that's the future, but this might be one application domain for artificial intelligence. So this was a research project making use out of Europeana corrections. There's another example where we are using a deep learning tool and this technology to identify, for example, inventory or registry numbers which you can find on objects or on label on the object. And on the right side, you see a camera picture from an object. The object is below. Here you have an object with encarved numbers. And now the challenge is the numbers has this object has encarved numbers to take a picture of this. So you need high precise cameras. It's a little bit different compared to archival materials where you have a static lightening and a static material. Here in this object, you have different backgrounds. So the lighting is quite important. And the challenge was to identify, if possible by 100%, the number on this object. And the first trial of my staff was to use convolutional neural networks on this. But this was a totally failure. And then we looked into traditional tools. For example, for optical character reading, there exists in the 90s of last century the tool Tesseract, originally invented or developed by HP, Hewlett Packard. Then it was put in open source. And I think Google has used this or still is further developing this. And since version 4 of this tool of Tesseract, you have an URL below. This system is also using artificial intelligence methodology. And after the failure of using a convolutional network, we have quite success using this tool. And this tool is using another type of an artificial neural network. It's called LSTM, long short-term memory. You can find in the internet the documentation on this. And the short outline how this tool is working. We are taking pictures from the object, which is here on the right side. And then we take this picture and we stretch it to bring it in a linear form. Then we send it after some pre-processing and after managing the database behind. We send it to Tesseract. And then you see on this table on the left side, there are 22 rows. And each row belongs to a position of this number. And we have, for example, row 12 to row 22, probably. Then you see, so that it was an outdated overhead, but here you won't see it. But here you have the numbers 37352-32-N. That is part of this reference number, and it is exactly identified. So that's quite good, but not all characters have been identified equally. For example, if you look on column 12, column 12 eventually should be a T, and it's not a T, it's an E, I think here. So that is where the deep learning and the labeling process comes into place. So a practitioner working in our office was hired, and she did correcting all these wrong identified characters. You see, all these characters, or part of these characters, have not identified correctly. And so this girl, it was a lady doing this, entered the correct character into this column, and then this table was sent back to the database. Tesseract is working, And after some iterations and after some training of the network was identifying these numbers correctly. This is an outcome of an industrial project. You know, this the object as screws, and this implement as screws used in the medical field for implants. And the problem here is a mass problem. We have millions of screws all over the world. And now how to identify these screws that are not enriched, that are not inventory numbers, that are so-called lot numbers, which are used during the production process. So the challenge was here to have really 100% identification. And if it's done in the medical field, you are not allowed to make any errors. So that was really a challenge. And this project is still going on because all optic and other methodologies are not mature enough to make this, put this in a professional environment. So this is one part of deep learning. You can use it to identify labels on an object, for example. Another example, how you can use artificial intelligence, for example, in paleontology or on archaeological sites, how you can identify substructures. The substructure could be the map of a town, of the houses in the town, or if you are looking in the biodiversity field where we have animals, where we have plants, we can look in the nasal cavities of a fossil, for example, and to reconstruct the cavities in a fossil. What you see here is not a fossil, that is a nasal cavity of a real, of a human being. And everybody of you has such a thing in your head. And the challenge was using, and here I have used a convolutional neural network to identify the different parts of the nasal cavities. The human being has 4 different cavities. An animal, for example, has 7 different. So if you have a CT, a computer tomographic scan of a fossil, for example, you could reconstruct the cavities in the head of this fossil. And if you look here, you have not really identified everything correctly. For example, that is a frontal sinus. You have here part of the other sinus that is in purple, and you have this purple point in the red side. So the system was not exactly identifying the cavities, but it's close to be, it's up to, if you are counting the points, it's up to 99% correctly done. So again, that is an example in the, which comes from the medical area. If you do a diagnosis, computer-assisted diagnosis, you have to do precise as possible. You are not allowed to make any error. Otherwise, you are killing people. So that's not very nice. So this is an application of artificial intelligence. It comes out from a 2-class classification. So the first step in this project was to separate air from not air, or you have sand or not sand, if in the archaeological sites, and how to separate the B classification, separating 2 materials. And here you have already a 9-class segmentation, where we have different structures, and each structure is represented by a class of objects. In this case, we have around 3,000 CTs from 3,000 patients. And this is still an ongoing project where in future the medical doctor can be assisted by the computer. And as you know from archaeological sites, these methodologies and these tools coming from the medicine are also used in the museum area if you have mummies, for example, for reconstructing and other things. So that is a classification problem, or a solution of a classification. And that concludes this small part. My time is not running here, but I think I have some minutes still left, isn't it? Okay, so I come to the next chapter of my presentation. It's edge computing. I have one slide taken out from Wiki. Wiki is good enough for this introduction. And if you look into a three-layer concept of the IT global infrastructure, if I may say so, then we have, for example, the cloud. The cloud means it's a centralization of some thing. For example, the Europeana catalog is in the cloud, and we can call it a central catalog. So it's a typical cloud-based application. Then at the end, at the edge of the cloud, that's where the name is coming. It's more or less the peripherals on the clouds. You have computer systems, so you have computers which are delivering and generating data to the cloud, for example. And this is something like a middle layer between, if you look at the museum side, between visitors and between the cloud facilities. For example, in the museum, we can put on the edge a localization system. How this can be implemented. For example, if you have a very famous building, like in the Dutch Rijksmuseum, you have some very famous paintings, and you can program a tour guide with a map of the museum, and you can localize their position with GPS or any other methodology of a visit in the museum, and guide the museum to this object or to any other object. So if you have the interest profile of a visitor stored in the tour guide, then you can dynamically change the path to an object of interest. So that's a localization system. And here another technology can be used, for example. I did a presentation 20 years ago on that. That is a localization system based on a radar system, on an impulse radar. That is a technology which was opened by the American Ministry of Defense after 9/11, 20 years ago in New York. And it is a system which can look below the Earth, can be look through walls. So that's important for intrusion. And you could use it now if you want to calculate distance between two visitors. So in this pandemic time, it's a very good technology. I'm just doing some research on how to substitute X-ray based procedures like computer tomography, substitute this or use another technology based on ultrawideband. And then you have on the final level that are the peripherals connected by a local VLAN and a mobile network connected to these edge computing devices. So you find a lot of material on this. And I give you some examples. Here you have already an example. That's a localization system for tour guides, for example. The technology behind is called two-way ranging. So if you are interested in more details. And I have shown you some objects below when identifying the numbers. And here you have such a device. You can call it an Internet of Things device, which you can connect to the internet. You have here on the right side a plate with different objects. This could be small animals, it could be small plants, something else. We have here a set of screws. And we have here a camera system. So this is a whole optic with a microscope and anything else. And this is mounting on a device which is controlling the movement of the camera here. So you can computerize it that way that the camera is moving automatically from object to object, takes the snapshots, analyzing the snapshot using artificial intelligence and so on. So you can build in the intelligence already into the camera. Then you can get something like you can call a smart camera. That's a quite interesting thing. It would save time if you are digitizing objects which are arranged, for example, on a plate. And then you have the microcomputer. So this is all an edge system. And it's a device of Internet of Things. We have here a microcomputer. If you're interested, it is a Raspberry Pi with a big power. This computer is connected to another computer. That's also a microcomputer, Raspberry Pi Zero, which is controlling the cameras. And the whole thing is delivering data over the internet to a cloud-based system, for example. And here you have the remote control, the graphical user interface, which is installed remotely, and where you can control the movement and the movement of this device here, of these cameras. And here you see the outline, and you can here already identify what you have collected here. So this is a good help for digitization processes. I'm aware of a German company who has developed a device for digitizing small animals, for example. And the computer, you see as a Raspberry Pi 4, the latest edition, which has the power of a normal PC. And the software is patented if you are interested in the technical details. And this I come to my last slide. And I think I'm within my time limit still. And to say the last term I will introduce you is the term digital twin. So the digital twin is defined by the Object Management Group, OMG, and this group is running courses on this. And the digital twin is not only a virtual copy of a real device, it's also representing the dynamic part. So, for example, if you go to Milan, and so you have a nice science museum, it's a Museo di Storia della Scienza, and here you have a very good exhibition of the sketches Leonardo da Vinci did some 100 years ago, but Leonardo was not able to develop this. And but now, in the last decades, for example, people started to develop models of these devices. For example, here you have a gear wheel. And this was the original concept of Leonardo. That was a model. You can download this printed. These white parts are 3D printed. You can download it from the internet somewhere. And then you can make a copy, a replica of this sketch. And here you have a handle. And if you put on the handle an actuator, we call it, for example, an engine driving this handle, then you can move this thing. And what I cannot show you, we have no virtualization of this device here. But once you have it, you can, for example, drive this using this device. And this device afterwards is controlling this engine, and this engine is controlling this device here. But on the other way, there should be sensors delivering information back to the virtual thing. Another good example now is nowadays are the windmills, offshore, for example, where you have virtualizations of the windmills in the computer center, in the control center for the windmill park. And then the windmill have a lot of sensors sending data back to the digital twin. And on the digital twin, you can simulate something and send commands back to the real thing. I also have made a small sketch, but it's not time enough here to use this in the medical environment. you can virtualize the patient, and with an endoscope, with a camera, you can look into a patient, and then you can overlay the camera with a virtualization of the human being, for example. So that's one part interested for Science Museum, and this completes, and sorry having used too much minutes, this concludes, if I find the right button, yes, of my presentation. Thank you very much.
Thank you.